Welcome to Hyperfixation Investigations, the podcast where two neurospicy best friends take time 2 Saturdays a month to info dump their research deep dive of the week.
Lovingly produced and copyrighted by Wolf and Stag Productions.
Today's fun fact is, white holes are hypothetical opposites of black holes. They're believed to expel matter and energy, but there's no experimental evidence for their existence as of yet.
Good morning, I'm Josh, and I will be captaining today's episode, Black Holes.
Good evening, I'm Kara, and I'm just along for the ride. For those of you joining us for the first time, how things work around here is that Josh will be leading us through a mini lecture on the topic, and we will discuss today's topic and any questions we might have.
Expect tangents throughout. We switch off duties each episode, so next time, expect Kara to take the helm.
Now to our regularly scheduled program. Josh, what have you been hyperfixating on this week?
The void. The vast empty of outer space. Stars, galaxy, nebulae, the heat death of the universe, everything and everything in between. But also, I need to actually focus or narrow in on one thing to talk about for an episode.
Just one?
Well, usually. So I figured I would actually just talk about black holes today.
Nice.
Since they are one of the most evocative and fascinating types of objects in the universe, in my mind.
Agreed.
So, yes, it's finally time for a black hole episode. My goal is to get into what black holes are, what their life cycle looks like, and some history will be interspersed throughout. Eventually, of course, hopefully, we will get to some representation in media, both good and bad.
Nice.
And firstly, I just want to say, I know black holes can be a lot. there is going to be kind of a lot today. But I promise they're not necessarily as esoteric as sometimes they first appear.
Yes.
Yeah, we'll get into it. So first things first, what is a black hole? Basically, essentially, it's just a massive celestial object that has so much mass that its gravitational pull is utterly inescapable.
Yeah. It's one of those concepts that I've now watched enough documentaries about it and whatever that I get it, but I don't get it.
Yeah, well, because the thing is, it's actually pretty straightforward. It's just that
it's hard to wrap my mind around the fact that can be how physics works, though.
Yeah.
I think.
Right. Okay, if we start somewhere simple, like if you add more mass to an object, it exerts a stronger gravitational pull, right? Like on Earth, we feel a certain amount of gravitational pull, but we would weigh more on Jupiter because Jupiter is larger and exerts a stronger gravitational pull.
Right.
And we would weigh even more on the sun because we would feel the gravitational pull. It has much more mass, stronger gravitational force. So it's an extension of that same concept, just at an extreme.
Yeah.
And these black holes are not simply large and heavy, but also incredibly dense and compact. And they're such an extreme that they are able to capture, and I mean truly capture, light.
Right. Which is wild.
Yeah. If anything gets close, and I mean anything gets too close to a black hole, it's falling in and it's not coming back out. Doesn't matter if it's moving at the speed of light, which you'll remember is the speed limit of the universe. Nothing can move faster than the speed of light. So if even light cannot escape, neither can you. A side note, the speed of light is exactly 299,792,458 meters per second.
Great.
Which approximately 641 a million miles per hour.
So a lot.
Yeah. For most situations, though, the speed of light is usually estimated at 3 times 10 to the 8th meters per second or 300 million meters per second.
Okay.
Because it's close enough that for most math, it gets the job done.
Good.
Right?
Good. Yeah.
Now, generally speaking, Einstein gets credit for predicting the existence of black holes as part of his theory of general relativity in 1915. Technically, John Mitchell in 1783 made the first documented prediction of black holes existing that I'm aware of. But John Mitchell gets rather forgotten because he was working under the assumption that the speed of light is not constant, which it is. He just didn't know that. So despite his calculations being actually pretty good, Einstein generally gets credit because his very many equations and theoretical understandings were not only spot on, but remained culturally relevant. And the theory of general relativity was extremely comprehensive. And
yeah, you hear it mentioned all the time.
Yeah. And so, for the sake of today, I'm not going to get too deep into general relativity.
Okay.
But very basically, general relativity treats space and time as inseparable. Space-time is the fabric of the universe itself.
Mm-hmm.
And when discussing gravity, you can kind of treat it like a flat plane where gravity is just large, massive objects warping that plane.
Mm-hmm.
So if you have like a trampoline, you put a bowling ball in the center of the trampoline, right? You create a depression in the fabric that if you roll a ping pong ball on the trampoline, the path of the ping pong ball will be inevitably directed towards the bowling ball. Or if you just move it really fast so that it doesn't fall inwards but just flies off, it's still going to curve towards the bowling ball. Or it's going to be curved around it in some way. We're basically just applying that idea to the universe and gravity. So we sometimes will hear that referred to as like a gravity well that pulls both mass and light towards it.
Cool. And
thus, black holes are a byproduct of this line of thinking, leading people to realize that it must be possible for an object to be so massive that it warps space-time beyond the ability of light to escape that object.
Okay.
And again, John Mitchell, who I believe was an English country parson, and, the mathematician Laplace had also theorized the existence of black holes.
Mm-hmm.
They didn't call them black holes. If I remember correctly, the name black hole didn't really start coming into use until the 1960s, like the late 60s.
Yeah.
Before that, they were sometimes referred to as dark stars, collapsed stars. They had a few different names that were bandied about.
Yeah.
But black hole is the main name today. And that name seems to originate with physicist Robert H. Dicke, who in the early 1960s compared black holes to the Black Hole of Calcutta, which was a notorious old prison where people went in and never left alive, that kind of thing. But there were various people throughout the early to mid 1960s who started using the term a lot more often. So various astronomers and physicists started adopting the term, and it's possible that it just kind of caught on naturally. Anywho, mathematically speaking, there is a point of infinite mass at the very center of a black hole.
Yeah, that's part of the thing.
Yeah, and that's where it gets really like that feels wrong.
Yeah.
That is what's referred to as the singularity.
Okay.
So when people talk about a black hole and refer to it as a singularity, sometimes we talk about the black hole, the whole thing, as a singularity.
Yeah.
Kind of, but technically not really, because singularity is just the point at the center.
Right.
But also defining exactly how much of what we see is quote unquote the black hole gets weird.
Uh-huh.
So, calling it a singularity, it's forgivable. Now, the point of no return for light around a black hole is known as the event horizon.
Yeah, that's what makes the cool pictures, right?
Yes.
Yes.
Yes. Great movie, by the way. Love Sam Neill going completely mad while Lawrence Fishburne and his crew just try to get out of Dodge.
Nice.
Fantastic horror. Anywho, I think I actually mentioned that movie for the same joke in the Star Life Cycle episode.
Probably.
But I can't help it. It's right there.
Yep.
An event horizon is sometimes described or defined as a point beyond which events can never be observed.
Okay.
Right, which makes sense insofar as that is the point from which nothing can escape. And since our eyes and cameras use light to gather information, specifically light that is bounced off of something and then bounced towards our eyes or camera photoreceptors, we need that reflected light to be able to see something. So if light falls into the event horizon, it's not coming back out. We can't see what's in there.
Right. Disappearing. Vanishing.
An event horizon sometimes gets defined in an even more arcane way, almost. Sometimes getting defined as the distance from the center of the black hole at which there is no traversable path that light can travel that will result in its escape from the black hole. Which really just means...
Yeah.
Yeah, that's the point at which it doesn't matter what direction light travels, it's not escaping.
Right.
Which is also like, hey, how many ways can we describe the same exact thing? Now, the existence of the event horizon does mean that we basically don't know what it looks like inside of a black hole. And that has resulted in a ton of conjecture and, frankly, wild ideas over the years.
Good.
And science fiction loves to take that angle and go, what's inside? Is it a wormhole? Is it travel? Is it like micro universes? Is it travel to other dimensions?
I like all of the options. All of the above.
They're all very fun, but quite frankly, most of them are.
I want them to be paths to other universes.
I do too, but quite frankly, like it's science fantasy until proven otherwise, in my opinion. Because, I mean, really, it's just a bunch of super condensed, superheated matter.
Yeah.
Probably.
Be boring about it.
Yeah. Yeah, okay. Hey, the boring answer right now is just that we don't really know.
Yes.
What the true inner visuals of this object are.
Well, it's like we talked about yesterday, which probably won't even make it into yesterday's episode. Will be in a future
yesterday's recorded episode, which will come out after this episode.
Correct.
Yes.
And has tangents that are not going to make it into the final edit.
No.
But the whole crossover that we had mentioned of like my idea that in my personal belief system and spirituality that like magic is just science we can't explain yet.
Mm-hmm.
I feel like a lot of science fiction ideas are also just science we haven't figured out yet.
Yeah, in a way.
You know?
Oh, yeah. Now, when I say that something is massive,
yes,
usually I'm, at least in this context, I'm usually speaking in astronomical terms, and I'm just stating that something has mass.
Okay.
It's made up of matter, and in this case, that matter is compacted to a ridiculous degree and made up of an insane amount of mass, but they do actually generally take up less like physical space than one might expect for how much stuff they have crammed up inside of them.
Right. Because it is all being like super condensed.
Yeah.
And stuff. Yeah. Okay. That makes sense.
Yeah. So to put it into perspective, the sun is estimated to have a mass of 1.988 times 10 to the 30th kilograms.
I'm just going to pretend any of these numbers mean anything to me.
And
it's okay to some of you listening if they don't make any sense to you either.
That's about 198 nonillion kilograms. Nonillion, as in there are 9 commas in that number.
Good.
There's so many zeros, there are 9 commas before you get to 198.
I don't like it.
It's a lot.
I don't like it.
It's a big number.
I don't like numbers on a good day.
Yeah, well, okay. I'm not going to refer to this number directly. I mean, I am going to refer to this number directly, but for now,
yes,
we don't need to refer to 1.988. I'm just going to refer to that as a solar mass.
Okay.
It's the amount of mass that our sun has.
Got it.
It's a solar mass. And the smallest black hole that we know of, at least that I could find, is at least an estimated 3.3 solar masses.
Okay, now, are those primordial black holes?
No.
You have a space nerd for a friend, so I asked space nerd questions.
Okay, so primordial black holes, technically speaking,
because I thought they were small,
aren't proven really to exist. It's something we're looking for.
Yeah.
But primordial black holes, for the sake of the listener, are black holes that are expected to have popped into existence within the first few seconds of the universe's existence, like immediately following the Big Bang. And we haven't found necessarily any evidence that these do exist. We expect that they should, but we haven't found them yet. Which isn't to say that they don't exist. It's just, we can't prove it yet. And it could be that they've just made themselves very elusive over time. And it could be that they're just fewer and further between than we would expect. But again, we haven't found primordial black holes yet. Though I will in a second get into a couple types of black holes.
Cool.
Yes. But no, that 3.3 solar mass black hole, that is according to a 2018 study which looked at the orbital period of a red giant star and found that the movement of that star mathematically implied the existence of a companion with a mass approximately 3.3 times the mass of our sun.
Okay.
And since neutron stars have always been observed at less than 3 times the mass of our sun, then it's a pretty reasonable indication that that's a black hole.
Interesting.
Yes. And this actually is how the vast majority of stellar mass black holes have been identified.
Yeah, it's funny how often with astrophysics and stuff like that and space discovery, it's comparison to other things that helps you figure out something.
Oh, yeah.
You know, because it's so hard to well, first of all, black holes in general are just hard to see if they're not actively eating.
Yeah, dark objects in a dark night sky. No, It's very easy to see.
Right. But yeah, I mean, it's the common thread, I feel like, in our episodes about space and stuff is this idea that, like, no, you really have to compare it to the size of our sun, or you have to compare something to something in which it's orbiting or in relation to, because it's so hard to find or see. And not just black holes, but like we have to do that with trying to find planets and all kinds of things.
Yeah, the amount that we just use, hey, what's the wobble on that star?
Exactly.
We can figure out what's orbiting that star based on the wobble that it displays.
Yeah.
What irregularities in its motion can we detect? Yeah. But stellar mass black holes are the first of the two main types of black holes.
Okay.
These are the smallest standard black holes, the runts of the litter, if you will. These black holes can range from a few times the mass of our sun to several tens of times the mass of the sun.
Yeah.
Stellar mass black holes are named such because they form from the corpses of dying stars. Which, if you ask me, is pretty metal.
Yep, totally.
Yeah. But their naming is actually super straightforward because they're formed from the mass of a stellar object.
Right. So they are stellar black holes.
Stellar mass black holes.
Yep.
Yeah.
Yep.
Now, listeners may remember in my episode on stars that we discussed the death of various sizes of stars.
Mm-hmm.
And I did specifically want to remind the listeners that when a star is dying, it is because it's run out of hydrogen to fuse into helium, so it begins to collapse because of the energy of those nuclear fusion reactions is what allows a star to fight the pressure of gravity. But because it's now collapsing, that star gets compressed and compacted strongly enough that it starts to fuse helium instead into carbon, which again pushes the star's mass outward, and the stars continue this kind of yo-yo effect until they either expand into a red giant or a red supergiant, depending on how much mass they have to start with.
Mm-hmm.
And today we're only really talking about the remnants of the larger stars.
Right, because it takes a certain large star size to even be viable to become a black hole.
Yes.
Yeah.
Yes. For stars with 8 to 20 solar masses, the supernova will explode into a nebula and leave behind a teeny tiny super dense core called a neutron star.
Right.
Which will remain relevant today. We'll come back to those, don't worry. But neutron stars, reminder, they're so tightly compacted that the electrons and protons have actually forced themselves together within the individual atoms and have created a star of only neutrons, or almost entirely only neutrons.
Right.
However, stars at least 20 times the mass of our sun will result in a black hole when they die. There's a moment in the yo-yoing where there's enough mass in such an incredibly small space that the pressure actually cannot overcome the force of gravity ever again, and it just collapses in on itself. So stellar mass black holes are these objects which began as at least 20 times the mass of our sun.
Okay.
These are thought to be the most prevalent and abundant types of black holes in the universe.
Makes sense. There's a lot of stars.
Yeah, there's a lot of stars. In fact, there's estimated to be as many as 100 million just in the Milky Way galaxy.
That's wild.
It sounds like a lot.
Yeah.
And it is, but
it is a lot.
Also compared to the size of the galaxy, that's not too crazy. The problem, as you alluded to earlier, is that they are difficult to find.
Yeah.
This is part of why one of the easiest ways for us to find stellar mass black holes is when they're in a binary system with other stars, like I mentioned with the red giant earlier.
Right.
In fact, sometimes we have found black holes in binary systems because they're feeding on their partner. Specifically, this is known as a X-ray binary.
Good.
X-ray binaries do not have to involve black holes. It's really just any binary system in which a star is being devoured by its partner, and that partner can be a black hole, a neutron star, even a white dwarf. But an X-ray binary gets its name from the fact that the matter that's being absorbed ends up releasing a ton of heat energy in the form of X-rays, which makes these really bright, luminous events in the night sky if you are looking with a camera that can detect X-rays. What's extra crazy about X-ray binaries, though...
Oh, gosh.
This is another way for stellar mass black holes to form. If a neutron star, specifically, collects enough stolen matter from its companion, it can belatedly collapse into a stellar mass black hole. Remember I said earlier that we've never detected really a neutron star above 3 solar masses?
Oh, because by then it turns into a black hole?
Yeah, by then it's accrued enough matter that it can just kind of shunt into, it collapses. So
stellar mass black holes either come about from the immediate death of the star that's big enough to just collapse in on itself fully, quote unquote, to become a black hole, or it's not big enough, but it's big and it collapses into a neutron star, and then the neutron star eats its neighbors.
Yep.
And eats enough of its neighbors that it then finishes the collapse into a black hole.
Yeah. Either its neighbors or a gas cloud that happens to be passing by and falls into its gravity.
Yeah.
I say eating. Yeah. This is kind of a personification. Obviously, it's not literally like Pac-Man.
No, but it's great imagery. It's very evocative.
It is, and it gets the point across.
Yeah.
There is actually a secret third option for stellar mass black holes, still involving neutron stars.
Okay.
It's when a neutron star collides with another neutron star, or sometimes with another just large star, but typically it's neutron star colliding with another neutron star that creates enough mass in that moment for a black hole. Yeah, it's great stuff. Next category, supermassive black holes. These are black holes with the same name as, yes, that one song by Muse. You know what?
I know it, but I can't hum it.
It's in the Twilight soundtrack.
I know.
Yep, good.
Do you know the original Twilight soundtrack is not on Spotify from the first movie?
Isn't
because
it?
it was under a different production company under the first movie, and they won't give rights to Spotify. So people have put together playlists of the songs to make the first album.
Of course they have.
And then they add the other 3 movies.
Of course they have.
That are on Spotify.
Anywho, supermassive black holes, and yes, that's their real name. Again, scientists were very to the point with naming these guys. These things are true behemoths.
Yeah.
They were first theorized in the 60s. Most large galaxies have a supermassive black hole at their center.
Ours included.
Yes.
Though ours is kind of small for a supermassive black hole, if I remember correctly.
You are literally like 2 sentences ahead of me.
I'm not even reading his notes this time, guys.
No.
I've just watched way too many documentaries on this topic. I have a space nerd for a mom, and that's all I'm going to say about it.
and a documentary addiction.
This as well, yes.
Yes. Oh. This is especially common for spiral galaxies, which kind of spin around the supermassive black hole at its center, though the black hole itself is not necessarily the true center and axis of the galaxy, but it is approximately at the center. The supermassive black hole at the center of our galaxy is named Sagittarius A star. And yes, you do pronounce the asterisk as star. I don't remember why that is per se, but Sagittarius A star is estimated to be approximately 4 million solar masses.
We love.
Yeah, and it has been captured on camera.
Yeah.
I will include a pic, obviously, in the blog from the NASA Chandra X-ray Observatory, which was able to capture an image of the X-rays emitted by the matter entering the black hole back in 2012. And actually, the fact that we can see the flow of matter into the black hole as well as we can is largely because it's practically next door, astronomically speaking. It's only 26,000 light years away to the center of our galaxy.
Which is not very far.
No.
At all.
No, 26,000 light years is very close, astronomically speaking.
Yeah.
Now, the first picture of Sagittarius A star isn't the first picture of any black hole. And in fact, the picture of its X-rays is not necessarily a picture of the black hole itself.
Right. It's probably more the accretion disk, right?
Yes. Also, that 2012 photo isn't necessarily credited as being the first black hole picture. I don't remember exactly why.
I feel like we were in high school or college when the official one did, right?
Yes.
Yeah.
The distinction officially belongs to the supermassive black hole M87
Yeah.
at the center of the Messier 87 galaxy, whose picture was taken by the Event Horizon Telescope, published in 2019.
Because if I remember correctly, isn't there a pretty young female astrophysicist at the head of that team? So
Yes.
It was really big when they accomplished that.
Yeah.
Yeah.
I remember actually talking about that during my brief teaching stint.
Oh, nice.
Yeah. Now, the first picture of Sagittarius A star was officially taken on May 12th, 2022. And again, by the Event Horizon Telescope. Obviously, I'll be putting pictures of both of these on the blog.
Yes.
Sagittarius A star is huge, but as you alluded to earlier, it's on the smaller side for a black hole.
Mm-hmm.
I mean, the smallest supermassive black holes are at least 100,000 solar masses, but the black hole at the center of the galaxy Holmberg 15A has been estimated to have a mass greater than 40 billion solar masses.
With a B!
40 billion with a B. Solar masses.
4 billion of our suns.
40
billion of our suns.
Yes.
Yes.
Yeah, so we know that supermassive black holes grow by eating stars and absorbing other black holes. And in fact, supermassive black holes can even collide and combine with each other when galaxies collide.
Mm-hmm.
Which, as a side note, the Milky Way galaxy will eventually collide with our neighbor, the Andromeda galaxy, in about 4.5 billion years. So we've got that to look forward to.
Nice.
Yeah.
That's wonderful.
We'll be dead by then. It's fine.
It'll be fine.
Yeah. However, we don't actually know for sure how supermassive black holes form. It's possible they formed from supermassive stars in the very early universe.
Okay.
Or maybe from clouds of gases that never even bothered to form into stars. They just collapsed directly into these supermassive black holes.
Yeah.
We're just not entirely sure.
Cool.
Though astronomers have been able to telescopically study galaxies far enough away that we know at least some supermassive black holes formed within the first billion years of the universe's existence.
So they are old.
Yes. And reminder that the way we know that is because if you look far enough away, you're literally looking back in time. Because a light year is the distance that light can travel in 1 year. The speed of light is fixed, so it is always going to be traveling at that speed. So, if you're looking at an object 100,000 light years away, it literally took the light 100,000 years to reach your eyes. So you're looking at it as it was 100,000 years ago.
So cool.
Yes. So that's how we get a lot of observations about the early universe, are literally just looking further that way. Just further? No, further that way. Now, some listeners might have caught that earlier I said stellar mass black holes don't get any larger, typically, than tens of times the mass of the sun.
Right.
And I also said that the smallest supermassive black holes are at least 100,000 times the mass of the sun.
So isn't there like a missing in between?
There is kind of an odd gap.
Yeah.
This is where the intermediate mass black holes enter the picture.
Okay.
Sort of.
What do you mean, sort of?
Well, intermediate mass black holes, they make sense, right? Over time, stellar mass black holes collide or collect enough mass to grow to potentially hundreds or even thousands of solar masses. But for some reason, these have remained oddly elusive.
Hard to find, huh?
Yeah. Now, it's not to say that we haven't found any. We have.
Yeah.
We found proof of their existence. It's just that they're much rarer than we would initially expect them to be.
Well, and isn't that part of how they were like, there's got to be a different way supermassives formed because
Yes.
there are so few intermediates?
Yes.
Yeah.
That there's such a big gap there, and there's so few intermediate-sized black holes that getting to supermassive status just by the standard means that any black hole grows doesn't make sense.
Right.
Now, in 2004, a multi-year debate began about whether or not there was an intermediate mass black hole less than 3 light years from Sagittarius A star.
Oh, interesting.
Yes, with the debate largely concentrating around whether or not there was enough noticeable effect on the orbits of the star cluster that is super nearby
Okay.
Sagittarius A star for about like 1,300 solar mass black hole to be nearby.
Yeah.
And I didn't find a verdict on that one way or another, but as far as
Okay.
I know, it was at least from 2004 to 2006, a conversation that was ongoing. And I believe the last I saw on that was that they weren't confident that it was there, and there hasn't been an update since. But again, it could be that I just needed to dig a little further. Yeah. If I find more on it, I'll happily say so. But it wasn't my focus for today. It was just a side quest.
Yeah.
Good morning, everybody. This is Josh from the editing room. Just coming in to say it looks like there actually was a paper published July 18th, 2024 in the Astrophysical Journal titled The Evaporating Massive Embedded Stellar Cluster IRS-13 Close to Sagittarius A-Star 2 Kinematic Structure. Long title, I know. But this paper does appear to provide evidence that there may be a intermediate mass black hole of approximately 3,000 some solar masses near the center of the galaxy in approximately the region that I was talking about in this episode. All right, back to the show. As far as verifiable proof, however, in 2019, LIGO, the Laser Interferometer Gravitational Wave Observatory, which is actually a pair of American observatories in Hanford, Washington, and Livingston, Louisiana, along with Virgo, which is also a gravity wave observatory lab in Italy. And actually, there is a third gravitational wave detector laboratory called Kamioka Gravitational Wave Detector, or KAGRA, in Japan.
Nice.
This trio forms our gravitational wave detector network.
Mm-hmm.
Though KAGRA wasn't involved in this 2019 discovery, but in this discovery, they detected a binary black hole collision between two black holes of approximately 85 and 66 solar masses, respectively.
Mm-hmm.
And they merged into an intermediate black hole of about 142 solar masses. So intermediate black hole, it's above 100.
Right.
We just saw these two black holes collide. It made a larger black hole.
Yep.
However, some of you that are very good at math will notice that...
It's not me.
Yeah, well, yeah, not you, obviously.
Obviously.
No offense, but, you know. Some of you will notice that means that some mass was lost in the collision. That mass was actually turned directly into gravitational wave energy.
Huh.
Yes. Which is actually how we detect gravitational waves, including the very first time we detected gravity waves nearly 10 years ago on September 14th, 2015, when two stellar mass black holes in a binary system collided. Since then, a few hundred gravity wave events have been recorded, with each being either a black hole collision or a neutron star collision.
Cool.
Yeah, it has to be something incredibly massive.
Yeah.
For us to detect any gravity waves, but yeah, fascinating stuff.
Yes.
I think now might be the best time for a break. So
you sound unsure of this, Josh.
We'll be fine. We'll be fine.
Okay.
We'll be fine.
Okay.
Yeah. All right, let's take a step back from the event horizon while we get a cup of cosmic tea. If you enjoy keeping up with black hole collisions and neutron star collisions like I do, I actually have an app on my phone called Gravitational Wave Events, which tracks and updates with the latest detected black hole and neutron star collisions, which generate detectable gravity waves.
Nerd!
Yes, thank you.
You're welcome.
The interface of the app is admittedly a little clunky for first-time and even semi-experienced users, but that's mostly just because there's a lot of technical data reported in there. So regardless, I think it's a really fun way to keep up with the latest from the LIGO Virgo KAGRA collaboration.
Very nice.
Yeah.
I love LIGO.
Yes.
And I'm very upset that they shut down some of the LIGOs.
Yeah, it's... I've got a lot of frustration there.
Yeah.
Yeah.
They're so cool.
LIGO's great.
I love LIGO.
It's great. Do we not enjoy learning about the universe?
We do.
Then why?
I know. Plus, it's just a cool fucking building.
Yes.
There's multiples, but still.
Yes.
All right.
But still, God, using a laser and miles and miles and miles of tunnels with mirrors to detect the tiniest
black holes colliding.
Yes.
Well, not tiny black holes. They were very large black holes.
Tiniest variations in, gravity itself.
Mm-hmm.
Fluctuations in space-time. Going, oh, hey, must have been a black hole over there that collided with another one.
Yep.
It's crazy. Love it.
But we don't want to track that anymore.
No. C'est la vie. C'est la vie.
No, I didn't like that.
You're welcome.
For For those who appreciate social media updates and episode reminders, please follow us on YouTube at Hyperfixation Investigations Podcast or on Blue Sky at HI-podcast. Or sign up for our email list at our website to ensure you never miss a thing.
And please leave a comment or review on YouTube, Spotify, Apple Podcasts, or even on our website. We love to hear from you and it helps us a lot. If you would like to contribute to us directly and help us continue growing, please consider subscribing to our Patreon. I also have to issue a brief correction.
Oh, goodness.
I don't remember which episode now, but there was a recent instance where I said that the Wrecking Ball dog monster in Mario,
Okay.
I said it was called a Chomp Chomp. That is incorrect. It is called a Chain Chomp.
Okay.
However, I do believe there is, oh no, and I can't remember now if it's the Super Mario 64 or if it's the Paper Mario. In one of those, I think, there is a golden Chain Chomp named Chomp Chomp. So I believe that's where that came from in my mind. But I apologize to everyone who was offended that I got the Mario creature
Reference wrong.
With that said, let's stretch ourselves back towards the singularity. All right, now it's time to get really weird with it.
Oh, great.
Yes, because black holes of all sizes are really weird. And there's actually a lot of little things we haven't really gotten into yet that I want to explore, even if only briefly for some of it. Firstly, I want to round out some of the anatomy of a black hole because I realized I didn't even mention accretion disks yet.
Yeah.
And accretion just means gradual accumulation or gathering that leads to growth. And since black holes grow by gathering matter that eventually falls into them, an accretion disk is just the matter orbiting and slowly falling into a black hole.
Mm-hmm.
They tend to take on a disk shape because objects orbiting or falling into various objects tend towards orbiting in a single flat plane.
Yep.
Because it's just the most stable position to orbit something. And this is true even with our own solar system. Granted, there's some, variation on the angles of some orbits, but in general, the planets of our solar system orbit on roughly the same plane.
Mm-hmm.
With black holes, these accretion disks do tend to be quite large and luminous. They literally glow because a black hole's accretion disk is a ton of gas and dust moving at thousands of kilometers per second.
Nice.
All highly energized and slamming into each other like the universe's most fatal roller derby.
Love it.
Yep.
Love it.
So a lot of that energy gets released from those gases in the form of various wavelengths of light. And this does mean that the accretion disk is typically the most visible portion of a black hole.
Right.
And the pictures we've captured of black holes are mostly identifiable by their accretion disk. Now, not all black holes have accretion disks, however, because, some black holes are just roaming the universe.
Right.
Or they've eaten through all of their available nearby source of growth. And that, of course, makes finding those guys much more difficult.
Yay!
Yeah. Though we can still find them sometimes due to gravitational lensing.
Okay.
Gravitational lensing is just an extension of what we mentioned earlier with the extreme force of gravity pulling everything towards a black hole, including light. So if a black hole has enough gravitational force to eventually stop light from leaving its mass, then there's also a fairly wide region around the black hole where light is simply being bent.
Huh.
It's not falling directly in. It's just being curved around, like the ping pong ball rolling along the trampoline, not falling towards the bowling ball, but just turning around a little bit and falling off elsewhere.
Okay.
And like the glasses on our faces bend the light to enter our eyes at a more favorable angle, the gravity of a black hole is bending passing light around and effectively towards itself. And for this reason, it's called gravitational lensing.
Okay.
Now, for this reason, the accretion disk of black holes should actually look really weird up close. So if you were near a black hole and facing a black hole on roughly the same plane as the accretion disk, the part of the accretion disk behind the black hole from your perspective would appear to be both above and below the black hole at the same time. But the light from the top and bottom of the accretion disk is actually curving around the top and bottom of the black hole.
Right.
Right. So you're seeing the back of the accretion disk bent upwards around the top and downwards around the bottom.
That's crazy.
Yes. So it looks
That hurts my brain.
weird. But it's just because the thing has so much mass.
Yeah.
It's just bending its own accretion disk's light. So it looks weird. And don't worry, some visual aids will be on the blog.
Yes.
And they're also easy to Google. But gravitational lensing can actually help us find black holes because if you take a picture of space, you can sometimes notice a star or galaxy looks stretched out in a weird way.
Okay.
Or you might even see the same stars and galaxies in a small area of a photo appearing more than once with different stretching. This is because the light from those objects is actually passing nearby a supermassive object, sometimes a black hole.
Yeah.
Gravitational lensing is not unique to black holes. It's just far more noticeable the more mass an object has, and thus it's common with black holes.
Okay.
Yeah. So sometimes light travels around a galaxy and is bent by that galaxy. And yeah.
That's cool.
Yes.
Are there
around
like
a star cluster.
Are there images of those too?
I will have some, yes.
Cool.
Also, NASA has tons.
Yeah.
Just in general. If you want to go find a huge gallery, NASA has a ton of them. And the James Webb Space Telescope and Hubble Telescope have captured so many wonderful images
Yes.
of gravitational lensing around galaxies and black holes and star clusters. God, it's beautiful.
We love so much.
Sometimes a black hole will have an event called a particle jet, which is just when a bunch of matter from the accretion disk manages to end up flinging itself away from the black hole in a tight beam on what is based on the accretion disk. It's basically at the north and south poles of the black hole.
Okay.
And it's moving some tight beam of matter away at very nearly the speed of light. Again, not quite, but very close to it.
Is this what the documentaries I've watched mean when they say it's burping?
Probably, yeah.
Yeah.
Yeah. Without having watched those myself, most likely.
Yeah.
Oh, this is also not to be confused with quasars.
Okay.
Quasars are known as an extremely luminous active galactic nucleus, or AGN, active galactic nucleus,
Okay.
which really just means that the accretion disk of a supermassive black hole has heated up so much that the material very near the black hole is emitting a nigh unfathomable amount of light, often in the form of radio waves, which sometimes outshines the rest of the galaxy that surrounds it.
Jeez.
Yeah, it's not uncommon for particle jets or X-ray jets to be seen as part of a quasar,
Mm-hmm.
but they are technically distinct.
Different things. Yeah.
Yes.
Okay.
Okay, so now we get to some of the really weird concepts surrounding black holes that I just really love.
Spaghetti?
Oh, we'll get to spaghetti, don't you worry. But first, I do want to address Schwarzschild radius.
Okay.
So Schwarzschild radius is technically a variable from an equation written by Carl Schwarzschild in 1916 as a response to Einstein publishing his theory of general relativity.
Yeah.
Sometimes Schwarzschild radius and event horizon get used interchangeably, but they are different things. It's just that the event horizon exists at the Schwarzschild radius.
Okay.
Yes. The Schwarzschild radius is the radius at which the escape velocity necessary to leave an object's gravitational pull becomes equal to the speed of light.
Got it.
Which sounds exactly like the definition I used earlier for event horizon.
Yeah.
But that's because this definition leaves out a key detail, or it really implies a key detail, which is that the Schwarzschild radius is a characteristic which can be applied to literally any object.
Okay.
Everything has a Schwarzschild radius, but most things aren't black holes and most things don't have event horizons.
So they don't.
Basically, the most fun way to think of it is that the Schwarzschild radius is the radius of a sphere that any mass would need to achieve to become a black hole.
Got
How
it.
tightly would you need to compress something to turn it into a black hole?
Yeah.
That's the Schwarzschild radius. If you compress the sun, for instance,
Mhm.
if you were to turn the sun into a black hole, which it won't do that on its own, it's not big enough, you would need to compress the entirety of the sun into an object with a radius of 3 kilometers,
Oh, jeez.
or 1.9 miles. To turn the Earth into a black hole,
Yeah.
it would need to be a sphere with a radius of 9 millimeters. Less than a centimeter.
That's insane.
Yep. And technically, you have a Schwarzschild radius. I have a Schwarzschild radius.
We all have a radius.
You get a Schwarzschild radius. You get a Schwarzschild radius. It's just, it's mostly like a fun thought experiment and otherwise a meaningless value for most small objects like us.
Right.
But you can technically calculate for any massive object, hey, what would the Schwarzschild radius be?
Sure.
The last two things I have today before we get into the media stuff relate to time weirdness and how black holes evaporate. Which one do you want to hear about first?
Time weirdness, I think.
Time weirdness?
Mm-hmm.
Hell yeah. That does bring us to spaghettification.
Yeah. Sorry, I had a stitch marker in my mouth again.
Yeah, that's fair. So, because you can't really separate space from time when dealing with things like black holes and the fabric of the universe, it just is space-time. If you have enough gravity to dramatically warp space, you have enough gravity to dramatically warp time. So, the closer you are to an extremely heavy, dense, massive object, the slower time will move for you.
Right.
Technically, we do see a teeny tiny itty bit of this on Earth with airplanes.
Oh.
Where clocks in airplanes move slightly faster.
Interesting. I didn't know that.
The difference is so small it basically doesn't matter.
Right. Otherwise, I think we all would have heard of it by now.
Right. But because we have computers that rely on exact timing.
Yeah.
If things are even a fraction of a second off, everything goes haywire.
Oh, geez.
So that has to be taken into account.
Yeah.
Right? And the same is true with satellites. There is a slight delay. And it's not just the delay of signal going back and forth between. It's also that, satellites experience time slightly differently than us.
That's weird.
It's so slight that it only
really matters.
I know, but
still, it's a weird concept to think about.
It is. It's very weird. But for that reason, if you were to approach a black hole, you would observe the rest of the universe suddenly moving by at a blur, effectively, and anyone staring at you moving towards a black hole would observe you kind of
in
slowing down and eventually stopping. But that is also where spaghettification comes in.
Woohoo!
Because if an outside observer is watching somebody approach a black hole, like if I'm on a spaceship and I'm watching somebody fall towards a black hole, I'm going to watch the tidal forces of the black hole pull that person into spaghetti, like taffy.
Good.
Because and I'm only going to see a little bit of this, because again, it'll be moving eventually so slowly that they'll appear to freeze.
Right.
But because the black hole is such an incredibly dense gravitational anomaly, that if my foot is a little bit closer to the black hole than my head, guess what's getting sucked in way faster?
Oh, jeez.
And you can see it's so wild how exaggerated that kind of stretching becomes. And we call it a tidal force because, much like the moon moving the tides on Earth, it is the gravitational force of another object affecting something about this object differently.
Yeah.
Depending on the location of stuff on that object. So literally, if my left side is closer to a black hole than my right side, I'm getting stretched and pancaked and then spaghettied.
Lovely.
Yes.
We actually do love it. It's a cool concept.
I love it. It's wild.
Yeah.
But spaghettification was first theorized by Stephen Hawking, actually. Or at least first, officially publicized and theorized. The other big thing then is Hawking radiation.
Okay. That I've heard of, but I don't know specifically.
So this was also theorized by Stephen Hawking in 1974.
Okay.
So, you know how sometimes people talk about the law of conservation of matter?
Yeah.
Hogwash. What people are usually thinking of is actually the law of conservation of energy.
Okay.
Matter is basically just a special form of energy that has mass, which on its face is already wild, but bear with me, right? Because if you burn a wood log, the ash at the end is not going to weigh the same as the log did in the beginning.
Correct.
But if you take into account the energy released in the form of heat and light, then add that energy as mass back to that ash, you would get the exact same energy as the log originally had. Like, those are equivalent then.
Okay.
This is actually what Einstein's famous equation of E equals mc squared means. It's just energy is equal to mass times the speed of light squared. Which, I mean, that's already an oversimplification of the actual expression. The actual equation is much more complicated. But that is basically what that's getting at. It's a little weird.
Yeah.
But
I'm following it, though.
Yeah. The thing is that this also kind of works in reverse. So if you have enough energy concentrated at one point, that energy can spontaneously transform into matter.
Oh.
Yeah. Which, when this happens, a particle is created with its antiparticle. So, yes. So yeah, we're getting to antimatter here. But bear with me. Stick with me. It's not as crazy as it sounds,
Okay.
Probably. Matter and antimatter annihilate each other.
Yes.
So usually there's not much to notice when a particle-antiparticle pair pop into existence because they just almost immediately slam back into each other.
Mm-hmm.
However, there is enough energy just outside of the event horizon for photon-antiphoton pairs to occasionally be created.
And that's like light.
Yes.
Yes.
So Hawking radiation is basically just what happens when a photon or antiphoton falls into the event horizon and its partner escapes and does not fall in.
Oh, okay.
Through this, a black hole can theoretically evaporate over time and very slowly lose energy in the form of photon emissions.
That's crazy.
For reference, a black hole of exactly 1 solar mass has been calculated to take 10 to the 67 years to evaporate, which that's 10 with 67 zeros after it. That's quite a bit older than the current age of the universe.
Right.
So it's not like we're ever going to really see this happen.
Yeah.
But the math checks out that it should be possible.
That's wild. These like supermassive, dense, hard to think about things just disappear.
Yeah. And before the concept of Hawking radiation, it was generally agreed that, yeah, once something approaches a black hole, that's it, dog. That's it. But it can lose energy. It's just that it happens so slowly, we'll probably never notice. Not really.
It's just, we're working on like time and size scales that are so
incomprehensible.
Yeah.
Yeah. Now, as far as representations in media,
yeah,
I do take a bit of umbrage with the 2009 J.J. Abrams Star Trek reboot.
Oh, I do too. It's okay. But for different reasons, but I do too.
Oh no, I share those reasons, most of those reasons too. However, there's a scene where a ship gets pulled into a black hole and we actually see it like
happen,
enter the event horizon, which it wouldn't. Like we wouldn't see that at least.
Mm-hmm.
It would seem to just kind of
stop and hover
in place because time dilation. The one thing they do get right about that, though, is that the villain notices himself getting pulled in. And, like, yeah, he would absolutely observe himself being pulled in because his frame of reference isn't changing.
Right.
It's just any outside observer wouldn't see that.
Right.
But, it's a movie, so I get it. But the other weird thing is that when they create a black hole at the center of the planet Vulcan, and it looks like the whole planet's, like, falling into quicksand? Why? What was the point there? I don't... It's just weird as hell.
Yeah.
Then, of course, there is an episode of Doctor Who.
Yes.
The Impossible Planet.
That is David Tennant's best 10 rage monologue.
Yeah.
I adore it. I literally don't I don't dislike the rest of that episode. But I spend the whole episode going, I just want the rage monologue. I just want the rage monologue.
Correct me if I'm wrong, that's the laws of time are mine, right?
Yeah, and the devil in the basement. And,
yeah. Which, there's a lot of that's like weird because there's somehow a planet being kept from being torn apart by tidal forces of a black hole.
Because of the protections on it, because some ancient species locked what we base the devil off of in the basement of the planet, in like the core of the planet.
Yeah, like the whole planet is basically a prison for something that could effectively be called the devil.
Yeah.
All right, man, sure.
And it's trying to escape. But if it does manage to escape, then the planet's going to get sucked in while there are still people on it. He makes it to the spaceship, I'll tell you that much.
He does. And you know what? It's great. I love Doctor Who. I love David Tennant. That one just kind of hurts.
I know. I will say this. As a space nerd, I'm a space nerd I would call you an astrophysics nerd.
Okay.
And me a space nerd.
Okay.
Because I like space.
Mm-hmm.
I like learning about space.
Mm-hmm.
The math and the science of space, whilst interesting to me, I can only get so far before my brain stops comprehending it.
That's fair.
So, and I feel like what I do know is wrong when I watch science fiction and stuff. Like the J.J. Abrams Star Trek thing, that annoyed me because I knew about that already from one of the documentaries I'd watched that Neil deGrasse Tyson was the host on. So things like that for sure. I will always forgive Doctor Who's wrong.
No, that's fair. I mean,
science.
In general, I'm willing to go out on a limb for Doctor Who.
Yeah.
Because, like any work of fiction, you know what? Sometimes you just need a plot device, and you just go,
And the
sure.
black hole was the way to do it this time around.
Weirdly, Star Wars hasn't too often touched black holes.
Mm-hmm.
Sometimes there's something like, oh...
Star Trek likes black holes.
Yeah, Star Trek loves black holes. There's honestly like too many things to get into here. But I think there was something in Legends of ancient and truly horrifying creature being trapped within a network of black holes.
Oh.
By which I mean like there's a cluster, like a black hole cluster
that
is trapping a creature that is horrifying beyond imagination.
Great.
So they went, let's trick it into that cluster of black holes and hope that it somehow doesn't escape. And so far it hasn't.
So far.
Yep. And I can't really fault the black hole like science or logic there because as far as I'm aware, they didn't directly contradict the nature of black holes, and they are using the gravitational force and the time dilation to their benefit. So you know what? Sure. Although Solo, the Star Wars movie about specifically Han Solo's,
yeah,
that one did briefly feature a creature living in the accretion disk of a black hole.
Huh.
And they use a black hole to slingshot themselves.
Yeah.
Which is part of why Han Solo's whole thing of the Millennium Falcon did the Kessel Run in less than 12 parsecs.
Right.
Is because they literally traveled less distance because they got closer to the black hole than any sane person would. Also, parsecs is a distance, not a time unit.
Yeah.
So saying, oh, we traveled this thing in less than 12 parsecs is absurd unless you are actually saying, oh yeah, no, we took a shortcut.
Right.
That's not a brag so much as they got too close to a black hole and somehow survived by dumb luck.
But isn't that like the entirety of Han Solo's personality? So...
Yes, but add a sprinkling of scoundrel.
Yeah.
So like, it fits.
Yeah.
It's just, it's funny with additional context. But otherwise, Star Wars hasn't done too much black hole stuff, which I kind of appreciate.
Sure.
Interstellar, however.
Oh God.
Of course.
I will admit,
yes,
I've never watched it.
That's fair.
I've played music from the soundtrack on the piano.
Oh, the soundtrack's great.
The soundtrack's amazing. My RA, my freshman year of college, obsessed with it. So I listened to it a lot because I was friends with my RA. But yeah, no.
I think Interstellar's good. It's just, it's overhyped.
Yeah.
However,
yes,
it is one of, if not the best and most accurate visual depiction of a black hole I've ever seen.
Okay.
Between the gravitational lensing, time dilation, the accretion disk looks right. It's great. However, there's a bunch of wormhole stuff and like time travel within the center of a black hole. That's like, okay, that's space fantasy stuff. Sure, whatever. You need to tell a story. This is the story you're telling.
They are great plot devices.
They are. And, you know, we don't know really what it looks like inside of a black hole, so sure, do whatever you want.
Yeah.
And they didn't do any spaghettification.
Huh.
Yeah. But again, the accretion disk looked fantastic.
Nice.
So I'll give them credit for that.
Good.
And of course, I couldn't let myself do this without Treasure Planet.
Of course.
Yes. Because
one of the most expensive box office flops in history, but also one of the greatest animated films ever.
Yes. And let's be very clear. It was not advertised well.
No.
Because, you know, Disney was trying to use that box office flop as one of their excuses to kill their 2D animated department, because 2D animators were at the time unionized and 3D animators at the time were not. So if you can kill your unionized animator department to instead pay non-union animators, that's cheaper. So why not? And I will
Rude.
always be upset because there should have been 3 Treasure Planet movies.
Yeah.
And I've mentioned this before, and I will be forever salty about it.
I don't blame you.
Yeah. Yeah, there is a black hole that appears in Treasure Planet.
Yeah.
You know, the scientific accuracy isn't incredible, but at least they do have the star collapsed, it's going supernova, and it's collapsing into a black hole. That already is more than I would typically expect
Yeah.
from a movie that is actually a wooden sailing ship in space.
It's Treasure Island in space.
It's Treasure Island in space.
Yeah. Literally.
They just didn't change the vibes of the tech too much.
Right.
Because it's still, like, their plasma guns are flintlock pistols.
Yes.
It's great.
It's literally Jules Verne Treasure Island in space.
Yes.
We love it so much.
But they also don't have a spaghettification.
Yeah.
For a character who falls into the black hole.
Yeah.
And also, the ship gets way too close to the black hole, and they, like, almost fall in and ride a particle jet
out.
Yeah. You know, it's very fantastically presented.
Yes.
And I love it.
We do.
Again, because it's Jules Verne's Treasure Island in space, you can basically hand wave it as, yeah, they encountered a whirlpool.
Yeah.
Yeah, they encountered why not?
Yeah.
Yeah.
Well, honestly, the giant whirlpools that do happen in the ocean, I mean, they are obviously a different thing.
Yeah.
But they're not all so dissimilar.
It is a similar
They're
enough
decent metaphor or like analogies.
concept. As an analogy, it works well enough.
Like if you cross over the line into a giant whirlpool, you're not coming out until you're at the bottom of the ocean.
Well, you're gonna drown.
Yeah.
Yeah.
You're gone.
It's
There's a finality to that.
yes.
In the similar way, there's a finality to crossing the event horizon.
And lastly, Stargate SG-1.
The ultimate.
They had one of the best, like, black hole episodes of television I've ever seen.
Nice. Which episode was it?
Oh God, what was the name of it?
I don't need the name. I need a plot. I don't know the names of any of the episodes.
That was the episode where there was a team that they had stranded off-world that was attempting to escape from a planet that was being sucked into a black hole.
Oh.
But then the Stargate was stuck on because the time dilation.
Right. No, I do remember that. Yeah. Uh-huh.
Because, so the thing is, like, the Stargates are supposed to have an automatic shutdown timer, basically. After a certain, like, window of time, they automatically shut down. But because only a few seconds at most had passed on the other side.
Right. The rescue team couldn't get through because it was open. Right. I remember that. Yeah.
So they couldn't get through, and the team on the other side couldn't get through because the time dilation meant they looked frozen.
Yeah.
I really appreciate that despite there being wormhole weirdness all throughout Stargate,
always,
they did a great job with the localized time dilation.
Uh-huh.
And the fact that, yeah, people closer to the Stargate were experiencing way more time dilation.
Yeah, because didn't it like end up starting to fuck with the inside of the mountain?
Yes.
Yeah.
Yes. So people in the base near the Stargate sounded like really slowed down.
Right.
To the people outside.
Because there was this portal essentially opened that was a good episode.
It was great. And again, yeah, there's wormhole weirdness, but the fact that they were able to very well communicate time dilation in that episode, I really am grateful for and really respect, because that was good.
And that's using the real science as a plot point in a good way.
Yes.
And not just like the overarching idea of an object or, crackpot theories of what can be happening in black holes and all that.
Right. Using the black hole as a plot point and as a plot device with its real characteristics and trying to depict it accurately and realistically is great.
Yeah. I don't remember this specifically. So is the wormhole technology in Stargate based on black holes, or is this one of the representations where it's two separate things? Because there are some sci-fis where the black hole is the basis of the wormhole technology, and others where they're separate things.
Right. In this one, I seem to remember them being treated as separate things.
Yeah, I thought so too.
Where the wormhole technology is just some other thing that some other
where
advanced
you,
aliens
compress space-time.
Yeah.
And go through it or whatever.
Yeah.
Yeah.
There are some other issues with how the locations are designated that don't really make sense. But you know what? Whatever.
Whatever.
Sure, the constellations despite the fact that constellations change over time, and yet the constellations are the same, and they're also the same on every dialing pad around the galaxy, despite the fact that constellations would be very, very different on every planet. It's fine. Don't worry about it.
Hey, the Norse gods are little gray aliens, so what are we going to do?
Yeah, and the Egyptian gods were
symbiotes.
Parasitic worm aliens.
Worm things, yeah.
Using human hosts. You know what? It's very fun. And the pyramids were landing pads for their ships.
I love it so much. I love it so much. Every time I'm watching something on HBO Max or whatever, where a lot of the documentaries I watch at night are, Ancient Mysteries always pops up, is you might want to watch this. And I'm like, I already did. I watched Stargate. I don't need to watch Ancient Mysteries.
Yup.
Anything that shows me a pyramid and also shows space in the same image on their cover, I'm like, no, I've already watched this.
Yeah.
The writers of Stargate watched this for me.
Yeah, and the writers of Stargate did a better job with better ideas than your crackpot theories.
Yep.
All right. Unless you have anything else to ask, I have nothing else to add at this time.
I don't think so.
Then in that case, thanks for listening, everybody.
That's a wrap on episode 20, Black Holes. If you'd like to delve further into this topic, our research sources and related images are posted on our website, hyperfixation-investigations.com. Again, that's hyperfixation-investigations.com. Thanks so much for listening.
Follow us and drop a like, comment, or topic idea on Blue Sky and YouTube for updates, and check out our Patreon to support us directly, join our Discord community, and receive other special perks.
See you next time, and remember, what's a little info dumping between friends?